Hello. Since we've now finished up our discussion of constant velocity, we're going to move on and start discussing constant acceleration. And in this course, the only kind of acceleration we're going to be dealing with in terms of calculations will be a constant acceleration. Acceleration occurs whenever there is a change in an object's velocity. Okay, we know that velocity is defined as an object's speed plus its direction. So whenever we have a change in either one of those things, either the object's speed or its direction, there will be an acceleration that takes place. So there's three possible accelerations that we can discuss. First off, an object speeds up, so its speed gets faster. It slows down, so the speed gets lower, or it changes direction. So it turns from whatever its direction it was previously. Okay? Our basic equation for acceleration is going to be the change in an object's velocity over the time period in which it changes. And this one occurs only, or this equation only applies when an object speeds up or slows down. Next unit, we'll discuss a special kind of acceleration called a centripetal acceleration, which is acceleration that occurs when an object is only changing direction. For our units for acceleration, we're going to look at our equation down here, and we're going to plug in the units that we already know for both velocity and time. Our units for velocity are meters per second, and our units for time are seconds. So our units for acceleration are meters per second per second. And if you think back to your algebra rules, if you divide a fraction by a value, that value will go into the denominator. And so we get a value of meters per second squared. So in this case, that's where the second squared comes from. That does not mean you square any of the numbers. It doesn't mean that anything else is really going to happen. It's just the second squared to make a shorthand notation, as the speed is changing at some rate every second, and that's where we get meters per second squared. We have four constant acceleration equations. I like to call them the big four, and we're going to start here with our first one. And our first constant acceleration equation is going to result from that general acceleration equation. So A equals delta V over t. Okay? In science or math, when we see a delta, that means a change, and that's going to mean the final minus the initial. Okay, so when we have an object that is accelerating here, it's going to go from some initial velocity, whatever that may be, to some final velocity. So it is either speeding up or slowing down. If we want to solve this equation for the final velocity, we're going to multiply both sides by t. And then we get AT equals VF minus V naught. And then we're going to add the V naught to the other side, and we're going to get our first of the big four. And that is the final velocity of an object is equal to whatever its initial velocity was plus its rate of acceleration times the time that it was accelerating. Okay, so there's big equation number one. VF equals V naught plus AT. Okay, so we have a couple new quantities here. Before we only dealing with V's as constant. Now we have some final V's and initial V's, which means that our V is changing. And of course we have our acceleration term as well. Our second of the big four is going to deal with the idea of average velocity. When we did average velocity before, we said V equals delta x over t, and we know that equation holds true for two conditions, either looking at a constant velocity or the average velocity. And for our equation here, we're going to think of it in terms of an average velocity. So let's put a little AVG there. Sometimes you'll see a bar over the V that represents average. We're going to just do AVG so we don't get confused. And in this case, if we're dealing with a constant acceleration, we can find the average velocity of an object that's undergoing constant acceleration by just finding the average of the initial and the final velocities. Okay, just like you would any two numbers. Just add them up and divide by 2. And the reason we can do that is because we're assuming that the rate of change is constant. Just like when you find the average of two numbers, you know the scale between those numbers is going to be constant as well. So we can plug that in here, and that's going to equal delta x over t. And we want to solve this equation for delta x, so multiply both sides by t, and we will get our second of the big four. Delta x equals an object's average velocity times the time. Okay, so big equation number 2. Delta x equals 1/2 times the quantity v naught plus vf times t, where 1/2 v naught plus vf is just finding the object's average velocity. Okay? Big equation number 3 occurs when those first two equations are combined together. So let's write those out just to make sure that we have them. Vf equals v naught plus at, and delta x is 1/2 v naught plus vf times t. Okay? And so what we're going to do is we're going to substitute in v naught plus at for vf, because over here on this side we've shown that vf equals v naught plus at, so we can plug that in over here for vf. And we're going to be working on this side at this point now. So delta x is 1/2 v naught plus, we're going to plug in our other relationship, v naught plus at times t. Okay, so now I have to do a little bit of algebra. We're going to combine our like terms, and our like terms in this case are v naught and v naught. So we're going to add those together. So delta x is 1/2 times 2 v naught plus at times t, and then we're going to distribute our 1/2 and our t through, and we will get that delta x is equal to v naught t plus 1/2 at squared. Okay, that is our third of the big four. Okay, notice that equation does not have a vf in it, while our other two previously did. Okay, that's going to be your determination for choosing your equations, is based on the variables in your givens and your unknowns, and figure out what equation relates those variables together. Our last of the big four I'm not going to derive for you right now. We'll see later on in the semester. We could derive it now, but we're not going to worry about it. It's a lot of algebra. I think it's pretty nitpicky. We'll see this one later on multiple times. And that equation is that vf squared equals v naught squared plus 2a delta x. So this equation does not have time in it. So if there's a relationship that you need to use that it does not involve using the time, this would be an equation that you might want to look at first. Even though you may need to do some substitutions later on, this one could maybe give you a little jumping off point. So vf squared equals v naught squared plus 2a delta x, an object's initial velocity squared plus 2 times its acceleration times its displacement equals its final velocity squared. Okay, so that's where those variables come from and what those variables mean. Real quickly, let's talk about how acceleration and velocity relate together. If the velocity and the acceleration are in the same direction, and how do we relate direction to our calculations here? Very good, the sign. Okay, so if the acceleration and the velocity are in the same direction, we can say up here in parentheses we'll put have the same sign, either being both positive or both negative. Then the object speeds up. Okay? So if they have the same sign, or if we can think of them just in terms of direction, they have the same direction. Remember, the sign is an indicator of direction. So if the velocity and acceleration are in the same direction, they will have the same sign and the object will speed up. Okay? If the velocity and the acceleration are in opposing directions, put direct opposite here, meaning they have opposite signs, then the object slows down, of course. Okay? So just a little rule of thumb there to make sure you remember how those two relate together. So if they're in the same direction, the object will get faster in that direction. If they're in opposite directions, that means the object will initially slow down, and then it may end up changing later on. But the object will slow down, and it could approach 0 if the acceleration lasts for long enough. Okay, so you have that those opposing directions that could cause it to slow down. All right, that's all we're going to talk about today with this. We'll work some problems in class and hopefully get some clarification on it. Thanks!